Hi guys, Dr. Douglas Gillard here once again. Let's continue with our continuing saga of the story of creating the human. We are now, I believe this is video number 4, and we got through the week of twos, and now we are starting the third week. This is a very busy week, and this starts a time period known as the embryonic period. Lots of stuff is going on here at the same time. Authors are all over the place on this. It's a very difficult story to tell, partly because so much is going on at the same time. It marks the beginning of the embryonic period, we said, and AKA is the organogenesis period, because at the end of this period, organs are going to start to be formed or not even at the end of this. We'll see. No organs are going to be formed in week 3, though. The embryonic period extends from week 3, which we're now starting, all the way to week number 8. The star of the show, without a doubt, in this whole period, and it only takes up a little portion of the week 3, is gastrulation. That is the star of the show. There's Adele, of course, the star of uh, the music industry, but she's not the star of the forming of the human, right? Gastrulation is the star. Here's an idea of what's going on week 3. This is Larson. He gave us a time point at least, which was nice. The other authors didn't. And so we're starting week number 3 right here on day 15. We'll start gastrulation, and we're only going to get up to about this. Now we're going to get to right about here. We're not even going to get that far. So this whole lecture is just on day 15 and day 16, and we'll bounce around a little bit, but this is just a small piece of week number 3. So without further ado, let's talk about gastrulation. Okay, so about day 14, day 15 or so, day 16, it all depends a little bit. But the definition of gastrulation, this is the process of converting our bilaminar disc into a new thing called a trilaminar disc. Not only that, we're going to form all 3 germ layers by the time we're done with this video. So gastrulation, let's not forget that it includes the creation of the primitive streak as well as the germ layer. So that's really what's going on here. Some authors include gastrulation. They include the nodal cord formation and even the neural tube. Other authors, but we're not going to say that. We're just going to say gastrulation is the formation of the primitive streak and the 3 germ layers. So this is what we're building. Remember, before we didn't have this green layer. We didn't have this indentation in the dorsum here of the bilaminar disc. So this is all the stuff we're going to build. All right, so let's get. This is actually a very cool picture, isn't it? So before we just had the hypoblast layer and the epiblast layers right here. That was flat. That's been cut away. There was a cavity right here. Remember, that's the amniotic sac, which was lined by an amnion. Down here we had a secondary yolk sac, even that's all cut away. Okay, so that's where we are. That's what we're going to do. Try to build that thing. Forming the germ layers. So everything I just kind of said, more specifically, after the primary streak is mature, we're going to convert epiblast and hypoblast layers that we had in week 2 into 3 new layers, and those are called the germ layers. Who are the germ layers? The epiblast is going to become the top layer, which is called the ectoderm, or the embryologic ectoderm. That's the official long name of it. I'm just going to call it ectoderm. Then we have a brand new layer. That's the sandwich layer right here, this green layer. So that's going to become the ectoderm. This is the mesoderm, or interembryonic mesoderm. And then we're going to turn the hypoblast layer down here into the embryonic endoderm. Notice we have a endoderm, or an embryonic and an interembryonic mesoderm, because it's sandwiched between 2 the two embryonic layers. Okay. Some fun facts, always nice, easy places for me to make questions from when I test you guys on this stuff. So fun facts about gastrulation. Can't go anywhere without a primitive streak, so that's the first thing we got to form. It is a very busy week. Week 3 is very busy, but this is the biggest event, the star of the show. Lots of stuff going on at the same time, so it's kind of hard to tell the story because two important processes are going on at the same time. And it marks the beginning of Morphogenesis More Chiropractic Board of Examiner book, right? So that's a name you chiropractic students need to know. Means development of the body form. More fun facts. So we also had a name change. Remember way back in, I think it was video 2, we talked about the zygote was named a morula after it became 16 stages. Then it developed a blastocyst cavity, which became the primary yolk sac. So we named the little tiny human a blastocyst. And now at week 3, it's no longer a blastocyst. It's called a gastrula because why? Because the star of the show for week 3 is gastrulation. So now our little tiny mini human is called a gastrula. Okay, and again, when you're in doubt, if you forget, are we in the blastostage, or are we in the morula stage? I can't remember. You can just call it an embryo, and you could still be correct. The real star of the show. The real star behind the scenes is really the epiblast layer. We'll see that these epiblast cells are going to kind of convert themselves, and a whole bunch of changes are going to occur. And these guys are going to actually end up forming all 3 of the germ layers from these cells right here. These are pluripotent stem cells, which means these are the real ones that embryologists are after. You could use these to grow a new liver. You can use them to grow a front tooth, an eyeball, a kidney, a new pancreas. These are magical cells because they can change into anything. So they're super, super flexible. Morph into any type of cell that you want. Okay, so let's start our gastrulation. Step 1 is the creation of the primitive streak. What in the world is the primitive streak? Kind of showed you what it looked like, but we'll build one here in a second. It's a super important signaling center. The cells that are going to make up the primitive streak have all sorts of different genes turned on. We'll look at some of the gene products, and those gene products can influence cells moving through it and direct them where to go and what to become. So super important that you get a well-formed primitive streak. And again, kind of where we're going, the modified epiblasts are going to move down through the primitive streak in order to form 2 of the germ layers. So you have to form the streak, and then you have to pass epiblast cells through it, and so they magically morph into something when they come out the lower side of it. And there's 3 components of the primitive streak. There's the primitive node, the primitive groove, and the primitive pit. The primitive node has some AKAs. Primitive knot, sometimes it's just called Henson's node after the person who discovered it. Okay, let's see how the primitive streak is built. So there's a word that's used, induction of the epiblasts. This is the start of the process. So induction means kind of a transformation. The different genes are turned on to induce something. So here's the story starts with the epiblast cells, specifically the ones that are located caudally and peripherally. They become induced or modified. Genes are turned on within them somehow, and they start to literally migrate into the midline of the epiblast. And as they all reach the left and the right, they all pile up in the very center line. They start to form a little mountain range, and that's the primitive streak. And again, the movement only occurs in the caudal region. This primitive streak occurs caudally, not cranial. Remember, not cranial. We talked about that last time. So here is the caudal end of our bilaminar disc. Kind of cut it off and blew it up. This is the epiblast layer here. This is the amniotic cavity. That's the sides are cut around. This is the amnion right here. And here we see that cells, which we can't see, but thousands of cells are moving and migrating into the midline from the left and right. And they're starting to pile up and form a structure here. And that is a brand new primitive streak has just been created. What is, if we take this and look under the microscope, what is this? These are epiblast cells that have migrated here. And it's not as easy said as migration's not as easy said as actually done, and we'll look at a whole bunch of changes that have to happen. There's junctional complexes that have these epithelial cells. We have to break these junctional complexes so they can move. But we'll look at that. That's coming up here in a little bit. So once the streak starts forming, now we've got some identification of which way's front and which way's back. So the caudal region, the streak starts caudally. The spot without any primitive streak, now we know that's the cranial aspect. And again, as I've probably said in the other videos, one really confusing thing about embryology is caudal is an AKA for posterior. Authors use these two things simultaneously. In the real body, that's not exactly true, right? Because cranial or caudal is an AKA for inferior in the human, and cranial is superior. But because the little creature here, the little zygote, or the embryoblast, or the morula, it hasn't folded yet, but when it folds, these will come into the correct orientation. Okay? So one more thing here, it's important. Now, once the primitive streak forms, we can identify the caudal cranial axis, or the cranial caudal axis. And all that means is now we know which way is cranial and we know which way is caudal because we can see this pretty easily with electron microscope. Does anybody know another way? How can we really have already established the caudal cranial axis. Anybody remember that one? Yeah, remember at the other end, the cranial end, we remember the AVE cells, anterior visceral endoderm cells. Those, I mean, are the first real caudal cranial axis kind of demarcation, but you can't see those. Those are an endoderm layer or the hypoblast layer, and so it's difficult to see those with electron microscope. Okay, what causes this migration? So who's telling these cells to do this? Why are they all coming to the center like that? First, so watch out, nerd alert, we're going to get into some gene products. So multi-step process. First we have Wnt3 gets turned on. So the cells that are about to migrate, before they can migrate, Wnt3 gets turned on. Wnt3 actually turns on nodal, which we've already talked about quite a bit. I'm not going to go crazy testing for these gene products, but the nodal for sure. I mean, some of these you should know. So nodal, Wnt gets turned on, that turns on nodal, and nodal gets the epiblast cell excited and makes it want to migrate to the midline to form the primitive streak. Okay, and again, this only happens caudally, right? And it doesn't happen cranially. So these gene products are said to induce the midline migration of epiblasts. Okay, what does induce mean? Stimulates. It turns them, it stimulates them to doing this action. And there's the anterior visceral endoderm we just talked about. Remember from the previous video, these cranial epiblast cells are blocked from making nodal by secretions that come up from the AVE cells. Therefore, they can't migrate to form a primitive streak. Remember that? Here's the AVE cells. Okay. So what actually blocks, this is a review from the last video, but it's important stuff. What actually blocks nodal expression in the cranial region? So which way's front and back? Which way's cranial? Which way's caudal in this? Well, we know that the AVE cells are always to the cranial. So this is cranial. This will be caudal here. And where's the primitive streak going to form? Is it going to form on the back? Because this is going to flatten out, right? We're going to develop the amniotic cavity right here. This will flatten out into a bilaminar disc. So the primitive streak will form back here. Why? Because the AVE cells have secreted specifically nodal agonists, and here are the nodal agonists. Cerebrus DDK1 and Lefty1 are all they're all gene products that turn off nodal, and they circulate and they float into here and they soak into these cells, and these cells can't secrete nodal, therefore they can't form a primitive streak. Everybody good with that? So again, these signaling molecules diffuse into the epiblast and inhibit nodal secretion. A review from the last video. So again, here's our picture. Just the kind of the back, the amniotic cavity has been cut away. The amnion's been cut here. So this is the dorsal part of the bilaminar disc. We can see the streak starting, so we know this is caudal. This will be the head region up here, and no nodal secretion here because of all those genes, those anti-nodal gene products have been secreted to shut all these cells off. Everybody good? All right, so now the primitive node. The primitive streak, by the way, it's actually grows, the cells keep piling in to the back, and it keeps pushing this end out further and further and further. Cells don't come in out here and form the streak that way. The cells actually keep piling into the back of this right here, and as more and more pile on, this gets pushed out like this. Okay, that's how that works. That's kind of the extension of the primitive streak. Let's see. So primitive node. So new epiblast cells arrive at the midline. The streak quickly grows cranially, or some authors say anteriorly. Once the length is fully formed, the tip of the cranial end begins to get really thick, and we start to get like a little club start type appearance. All these modified epiblasts are just pushing up to this area. And that little club-like thing is called the primitive node. It's a super important piece of tissue. It's got all sorts of extra genes turned on, as we'll see. The AK is again where the primitive knot, Henson's node, and the organizer. So you could say that the primitive streak itself, by pushing cells forward, induced the formation of the primitive node. Okay, so here is our little primitive streak that's grown out like this, and it's got a knot. This is an overhead view. We're looking straight into the amniotic cavity has been cut. There's the amnion, and there you can see the primitive node. So it's a major signaling center. The primitive node is super important with regard to significance. If this doesn't form right, you're going to have a deformed fetus. So very important this gets right. Major signaling center, it induces cells that migrate through it to, it kind of like makes little zombies. So if you're an epiblast cell and you're ready to migrate and you go through this down into the plane of the page, it's going to turn on a bunch of your genes and you're going to be a zombie. You're going to go where it programs. You might go up here from the prechordal plate. You might go back down here to form maybe the endoderm or the mesoderm. So it pre-programs cells that pass through it. Okay, it manipulates their genes as they pass through it. So it's a very important structure. Nerd alert again, there are 3 classic genes that are turned on. I'm not going crazy. I cut most of the stuff out here. There's even way more than 3 genes, but there's 3 classic ones that are turned on in the primitive node that is not in other tissue. So we have chordin. Chordin is important for neural induction. We'll talk about that, formation of the neural tube, in the next video. It also turns on this goosecoid. Goosecoid is also important for neural induction by itself, and plus chordin actually stimulates even more of this. Goosecoid is also important with developing sidedness. For example, the heart is normally on the left side of your body. It's not symmetrical, and the goosecoid has something to do with making organs grow on one side of your body and not on the other. Then we have FOXA2. This helps mature the primitive node itself. So when cells get up into the primitive node, FOXA2 gets turned on. And it is really important for programming cells that are heading anterior or heading cranial to the node, like the prechordal plate, even the forebrain and things like that. And this is also mandatory for formation of the nodal cord, which is another structure that develops cranially. We'll look at in the next video. So there they are, chordin, goosecoid, and FOXA1. They are genes that are turned on. Genes, of course, when I say genes turned on, I assume you understand the central dogma. Genes turned on, that means they can be transcribed, and you can make an RNA transcript that swims out of the nucleus, finds a ribosome. It's translated into a protein, a chordin protein, a goosecoid protein, FOXA2 protein, and some of them are transcription factors and some of them are flat out proteins, and that's understood, that you understand a little bit about molecular biology. Okay, now we have 2 other things that develop. We have the primitive groove and the primitive pit. So as more and more epiblast cells are diving down through the primitive streak, they start to form a groove, and that groove is called the primitive groove. And then there's a primitive pit. Same thing, as more cells are diving down through the primitive node, it starts to hollow out and it forms a primitive pit. That's about all that means. It's pretty nice. Another drawing. Again, that same view. We're looking at the dorsum of the bilaminar disc here. The amniotic cavity has been cut away. You can still see the amnion here. So now let me ask you, which way is cranial and which way is dorsal? Well, cranial can't grow a primitive streak. So this is cranial. This is going to form the head of the little creature, of the human, and this is caudal down here. So here's a nice primitive streak, and we can see the artist has made some depth perception, so we can see that's the primitive groove, and the primitive knot or primitive node should be bulging a little more, but then there's a tunnel that goes right through it. Electron microscope of a real human, and you can see the primitive groove quite nicely. You can see the primitive node is like a little club-like structure or uprising, and then you can't see the primitive pit, but it's inside of there. Now we know the body axes too, right? Once we get the primitive streak, we kind of already talked about this, but if this is the primitive streak on this side, so we know the left is this way, we know the right is over this way, we know the head is going to form over here because the primitive streak is not here, and we know that the feet and legs and everything else, everything caudal, is going to form over this way. So we have all these axes. Okay, primitive streak is ready. Are we ready to start making the germ layers? Are we ready to start creating the mesoderm and the endoderm and the ectoderm? Well, we got the primitive streak. What else do we need? We're not ready yet. The answer is no. Because we got to prepare the epiblast cells. Epiblast cells they're just regular old columnar epithelial cells. And remember from your histology that epithelial cells are held together along their sides by things called junctional complexes. and therefore, like the skin is full of, the carotenocytes are held together by junctional complexes on the side, like desmosomes. And so if these before these epiblasts can go anywhere, you have to break the bonds. You have to break the junctional complexes, and then we have to prepare the space beneath the epiblast layer because it's dry down there. We need to make it slippery so these cells can squirt down in there. So that's what we got to do next. High author confusion warning. Authors are all over the place. It's taken me literally forever to make these videos because the authors are so. I literally have to read all 4-5 books to get the story, and then I even have to go into the research to get the latest. Some of the top-notch embryology journals, which I can get a good story from to piece this together. So good luck if you're trying to read one book and figure this out. You'll never figure it out. Okay, Game of Thrones. So preparing for ingression, the breaker of chains. So you guessed it, we have to break junctional complexes. They're not really chains, but that's like the hottest show. I don't know about the finale, but I won't do any spoiler alert, but what a great series that was. All right, break the junctional complex. So again, the epiblasts are locked together by junctional complexes, and we got to break them. And who are the junctional complexes? The ones that hold, now the tight junctions, they're junctional complexes, but they don't hold the cell together. Remember from your histology, what do tight junctions do? They stop things from sneaking between the epithelial cells. They're the ones that are toward the apical region of a cell. Those aren't what we're talking about here. Those will pull apart no problem. They don't hook to the cytoskeleton like these guys. The zona adherens and the macula adherens. Those are the big ones. Those are also called desmosomes. So these are made of cadherins, as we'll see here in a second. Specifically, the cadherins of the zona adherens are called ecadherins. The cadherins, and that's the protein family. The specific type of cadherin is an ecadherin for zona adherens, and desmoglines and desmocolons for the desmosomes or macula densis. But they're both from the cadherin family. Okay, and these are the things that need to be broke are actually in the extracellular compartment. They hold adjacent cells together. Let's look and see. Okay, here's a little model. So here's a cell over here. This is the cytoplasm or cytosol of one cell. Cytosol of cell number 2. These are the lateral walls here, and they're held together by these things. So these are zona adherens, and they're made of these little, kind of like a rivet. It's like a rivet head and the rivet shaft here. And these, in the space between the cells, these rivet shafts are bound together. These ecadherins stick together very strongly, and therefore you cannot pull these two cells apart. They can't migrate unless you break these. And then we have underneath here, these are the macula adherents or the desmosomes. Same thing, except they don't have ecadherin. They have desmogline and placoglobulin. Or I'm sorry, they have desmogline and desmocolons here. Placoglobulin is back here. This is the cytoskeleton. We'll talk about that in dermatology. There's some pemphigus vulgaris and bullous pemphigoid are diseases where you get an autoimmune attack on these specific regions. So we'll talk about that again in 7th quarter. But anyway, this is what I'm saying. We have to break the chains. These are the guys, the junctional complexes within the intercellular space between cells. These got to be broken. And once we break them, now our cells can pick up and move. And it's not that we're breaking these things. We are turning off the genes that make these. And so these things just kind of peter out when they need to be replaced. They can't be because the genes that make them don't work anymore. So that's what happens. And that's a cute little snail here. Snail is the freer of the epiblasts. So to break the cadherins, you need a transcription factor to be turned on in our epiblasts that are destined to go through the primitive streak and primitive node. You have to turn snail on. It's not exactly understood how snail gets turned on, and it gets deeper than this, but I'm keeping it kind of basic for this crazy stuff. So snail gets turned on, and it literally decreases the expression. Snail turns off the genes that make the cadherins. And without cadherins, as they finally can't be replaced, no new cadherins are formed, the cells can't bind together, and now they're free to migrate when they get the signal. Now, they have to migrate inside, in between the hypoblast and epiblast, and that's a very dry place. So we need to make it slippery. To make it slippery, our epiblasts that are now broken and ready to move, they secrete fibronectin. So the genes that secrete fibronectin are turned on, so makes them a slippery little thing, so they can squirt down through the primitive streak and do what they're destined to do. We don't want them sticking together again when they get inside the bilaminar disc. They tend to stick together, so we secrete, or they secrete, hyaluronic acid, which also keeps them slippery, helps them slide down there. So two kind of slippery substances, hyaluronic acid, fibronectin, are secreted. Now they're ready. So yeah, are the epiblasts ready to migrate now? Yes, they absolutely are. They're free of junctional complexes, and they're slippery. And the space has been made slippery. So we're ready to go. Exciting, isn't it? So the great migration, our epiblast cells are going to slip down through the primitive streak and be programmed to go somewhere. That is called ingression. Ingression is just migration. Langman, I wish he would stay with the other major books. Tends to go off in his little tangents and create words, but Langman calls ingression invagination. So we got Moore, and Moore does this too sometimes too. So I shouldn't just pick on Langman. But we got Moore, Board of Chiropractic Examiner books, saying this migration is ingression. Great. We got Langman saying this important phase of gastrulation is invagination. So what's a chiropractic student to do? The only choice you have is you have to memorize both of these AKAs, which is unfortunate. These two chiropractic board examiner books should get on the same page and make things easier, but they don't. So got to know ingression is the AKA for invagination. It's an AKA for migration, which is more understandable. Okay, first the simplified story. So if you're in high school and just want to get a very basic understanding, let's see what happens now that these cells are prepared. So the first germ layer we're going to create is called the mesoderm. So all these cells that are prepared, their JCs are broken, they're slippery, they come into the midline and they dive down right through the primitive streak. Some go through the back of the streak, some go through the middle, some go right through the node, the primitive node. But they go through the streak, and then to form mesoderm, they don't have to go very far, do they? They just have to pry apart and start filling up the layer between the hypoblast, which is the green layer, and the epiblast, which is the blue layer. Remember, week 2, that's all we had. We didn't have any of this red stuff. This is mesoderm that's now formed. And basically, by cells ingressing down here, we have just created our first germ layer, and that's called the mesoderm. Next, after the mesoderm has been made, the cells go deeper and they start kicking out the green cells. Remember, that was our hypoblast layer. And they start giving them the boot, and they start squirting out the sides here. And so now these cells are going to become our second germ layer called the endoderm. super important terms for medical students, chiropractic, physical therapy students. Got to know these terms because each one of these germ layers is going to form different parts of the body and different organs in the skin, in your nose, in your brain, and everything comes from different tissue. But all three of these layers, everything in your body is going to come from all three of these germ layers. So we've just created the endoderm. The cells kicked out. Now this is a little confusing. Langman's the only one who really said this, but it makes sense. Remember back in week 2 we've talked about the extraembryonic mesoderm that formed. And it's slow to form up toward the top of the amniotic cavity. And one theory here, and Langman's the only one who said it, but it makes sense. These cells that get kicked out, those old epiblast cells, it's believed that they form extraembryonic mesoderm, but the part kind of above the layer of the bilaminar disc. Okay, so we kind of make use of them. Carlson says that a couple of them still stay embedded here, and they can get kind of morph into this new tissue. But okay, so we got a red layer, we got mesoderm, we got endoderm. One more layer, we got to create an ectoderm up here from these epiblasts. So that's the next thing that's going to happen. And that's exactly what happens. So after ingression has stopped, after these two layers are formed, mesoderm and endoderm, the movement of cells stops, and now genes get turned on, more genes get turned on in these cells, and it morphs them into a different cell type called the endoderm. And voila, we have our three germ layers are created, and our trilaminar disc is now created. And technically, we're done with gastrulation. So we have just created, again, an ectoderm, a mesoderm, and an endoderm. Super important concept, because as we go through the formation of the brain, as we go through the formation of the gut and the intestines and the spine and the heart, the cardiovascular system, all of those systems have something in common, and they all start, they all start by everything we're talking about right now. So it's very important that you understand this stuff, or you're going to be lost when we describe how the heart is formed if you don't understand what we've just formed here. Okay, now let's get a little bit deeper, because that's pretty darn simple, right? I didn't explain anything about how this stuff is going on. So let's dig. Let's get into the specifics. So the first thing that we need to back up and talk about is our epiblast cells. We broke the junctional complexes so they can move. We made them slippery, and now they migrate down through the primitive streak or through the primitive node. Something happens when they migrate down. There's other genes that get turned on, and they actually turn into something called a flask cell or a bottle cell, and they look like this. They're no longer an epithelial cell. They morph, metamorphosis into a new type of cell that is, it's a mesenchymal cell. Think of them, this is me, but think of them as pre-mesenchymal cells, because mesenchymal cells can become any type of tissue. And here's a great picture from Carlson, and you can see here's the epiblasts. These guys are all kind of moving into the primitive streak here. Their junctional complexes are broken, they're slippery, and as they start dropping down through the primitive streak, they turn into this weird looking bottle cell, and then they keep metamorphosizing into this weird mesenchymal cell. And mesenchymal cell's weird because it actually grows legs called pseudopodia. And now inside what's the mesoderm now, it can swim. It can move with these legs, and it can walk. Okay, this one's got to go far lateral and become lateral plate mesoderm. This one's just going to become paraxial mesoderm. This one's got to go all the way up and form the cardiac region. They can walk because of these mesenchymal cells. What's strange is once they come to their destined tissue, like once they get down here and they kick the hypoblasts out, they morph back into an epithelial tissue. So we get this weird epithelial to mesenchyme and then back to epithelial in some cases. So when you hear the word epithelial to mesenchymal transformation, that simply occurs when these cells are slipping through the primitive streak, through the primitive groove, and genes are turned on and they morph into these crazy tissues. Okay, everybody good with that? All right, so everything kind of I just said, I think. These bottle cells or flask-like cells, they pass through and beneath the primitive streak. They're converted to mesenchymal cells. As they do so, they grow these feet or arm-like structures called pseudopodia, and now they can crawl to wherever their pre-programmed destination. Remember, when they pass through the primitive streak, they get turned into zombies, and they're told, okay, you're going to go become a cardiac region cell, or they get programmed into where to go. Okay, and then that completes the epithelial to mesenchymal transformation. And we're going to talk about that again when we talk about neural crest cells, probably in the next video. Why do they migrate anyway? Who tells them to migrate? We didn't really even talk about that. So these cells don't just migrate by themselves. They have to have genes turned on to do this. So there's two big ones that are turned on, and you know one of them already, nodal. So the ones that are turned on to nodal, they get the itch to migrate. When they pass through the primitive streak, depends what region. If they pass through the back region versus the front region, if they get exposed to high levels of nodal when they go through the streak, they end up becoming endoderm. If they go through a part of the streak that has low levels of nodal being expressed, it programs them to become mesoderm. Okay, so we'll look at that a little bit more in a minute. So they express nodal, but they also go through nodal on top of that. Then there's one called the brachyury. Am I saying that right? Brachyury, or you can call it the T gene or the brachyury gene. That's super important as well. It helps with ingression, kind of programs the cells to migrate. It's also really important to make nodal cord. So you get mutations in any of the genes that makes this, and you will have a terribly mutated fetus because of this. Who's first? Now, we said in my story, I said the mesoderm was first, but that's not agreed upon. In fact, the authors are all over the place on this. Moore, for example, says that the intraembryonic mesoderm is created first, so that's the one I went with. But Larson says the endoderm is created first. He's not a board book, so I went with Moore for chiropractic students. But probably Carlson says they happen together. That's probably true. We got these things going on at the same time. All right, so let's get a little more specific about making mesoderm. Epiblasts leave, so if they leave the middle portion, so if they migrate through the middle portion of the streak, they end up staying between the epiblast and hypoblast as they accumulate. That's going to be mesoderm. So the epiblast cells that go through the middle portion of the streak and dive down, they are going to not get a big dose of nodal. Therefore, I like to think of nodal as like energy. If you have a lot of nodal, these cells that come from the epiblast, they get a lot of energy. They can go right through the middle layer and end up all the way down in the endoderm. But if they go through the middle portion of the streak, there's not a lot of nodal there, so they don't have that much energy, so they end up staying in the middle and becoming mesoderm. So that's our first germ layer. Here's a cartoon of that. It's kind of nice because we see now the amniotic cavity. There's the amnion. And this is what we're talking about. We got cells moving down through the primitive streak in the middle region. They don't have a lot of nodal. They weren't exposed to much nodal. So they end up staying, and they're going to fill this layer up right here with mesoderm. Everybody good with that? Pretty cool. Their secondary yolk sac. Hypoblast hasn't been converted yet. We're forming the mesoderm here. Okay, now before we get to the endoderm, the prechordal plate story, I really should have told that first, because this is really what happens. No, everybody saves this for later, even later than this, but I think I'm going to put it in right now. And the reason they save it is because, like this little baby, what is that, a orangutan, I think? Crazy picture, right? He's in shock because the authors are all over the place on this. Prechordal plate, some like Singh, the Indian authors, there's I Singh and V Singh, they both call it the prochordal plate. Our board book, chiropractic board books, they both call it the prechordal. All the big authors call it prechordal plate. Larson says it's one of the most misunderstood structures in human embryology, and you try to put the story together. It must have taken me a week to put just the story together here. So we still don't completely understand it because we don't have the embryos to study is the problem. So authors are all over the place. So Moore, one chiropractic board book, says it's a thickening of the hypoblast cells become thick. That's not correct though, right? Because this is going to happen cranially, and we know that the cranial structures, those are the AVE cells. So Moore is off on that one. Langman, the other chiropractic book, and Carlson got the story right on this. So this is actually the very first mesoderm is laid down. It comes through the primitive node and it goes forward, and that's what the prechordal plate is. So let's check it out. So it is formed by the very first wave of those epithelial cells that move down through the primitive node. These ones aren't going to the back, they're not going to the side. These are going straight up toward the head, cranial region, and they stay in the midline. But they're migrating in between, they're squeezing between the epiblast and hypoblast. When they get to the cranial region, they stop migrating just before an area that is even further cranial called the oropharyngeal membrane. So in here they pile up and they form a plate. That's known as the prechordal plate. Carlson calls it the head organizer. It's super important with some parts of the forebrain. Without this, it's got a whole bunch of different genes that are turned on in these cells. A second wave, we're going to talk about this in the next video, but a second wave of cells right behind this will form our nodal cord. Okay, pretty cool picture here. Cranial. Okay, this is a side view or mid-sagittal cut right through the midline, and we can see that we got epiblast cells that are, their junctional complexes are broken, they're slippery, they're ready to go. As they go through the primitive node, they turn into zombies. Primitive node tells them, you will be a prechordal plate. Yes, master. And they will go all the way up, and they start piling and piling all the way up, all the way up, all the way up. And they make it to here, but this is it. They start piling up here and form a plate, and that's the prechordal plate. Notice right underneath them, there's our AVE cells. There's an anterior visceral endoderm, which is actually contacting. Probably shouldn't have made this one. Should be yellow, maybe one more green back here. But there is some connection between the AVE and the prechordal plate. Okay, so that's our prechordal plate. Super important. You read the books, you're going to be completely lost on this. This forms between the top layer here, epiblast, and the hypoblasts below. So when you see those pictures in the book looking down, we see all the pictures looking on the dorsal surface here. You can't see this, right? It's in between. The oropharyngeal membrane is going to form right up here over the top of this. That's what you can see. But this one is, you can't see it because it's in between. See, like this author did. So prechordal plate. there's the primitive node. You can see the cells have migrated up here. This is the cranial part of the embryonic disc. This is the caudal because the streak grew here. And so these cells came up and they formed the prechordal plate. He put little dots around it indicating that it's actually deep to this top layer. Everybody good with that? So what's the big deal about this prechordal plate thing? Super important signaling molecule for the brain. One of the big pathways that's used is the sonic hedgehog pathway. The sonic hedgehog gene is turned on and making all sorts of products. Super important for the development of the forebrain in particular. Think prechordal plate, think forebrain, think sonic hedgehog. Those guys all to go together. It also helps, neural crest cells are going to be migrating, we're going to see in a while. It helps them kind of stay alive and helps the migration of them into the forebrain as well. It doesn't form neural crest cells, it just helps them with the migration process. That's the little Sonic video game I think I see my grandkids playing around with. I don't even know if they still play this. Isn't that kind of old? I think our kids actually played that when they were growing up. Let's form the endoderm. Okay, so that's the end of the mesoderm. That's all the deeper I'm going to go in this video, but we got paraxial mesoderm, lateral plate mesoderm, intermediate mesoderm. We got the cardiac. We got a lot more work to do with that mesoderm, but we'll save that for the next video. Let's finish off the embryonic disc, make these last two layers. So the endoderm, we kind of said that already, but the cells that were exposed to more nodal have more energy. They go right through the mesoderm and they hit the hypoblast layer and they kick those hypoblast cells right out of there. And this, where this nodal is, they go through the cranial portion of the primitive streak. They don't go through the primitive node, but the cranial portion has a lot of nodal being secreted, so they pick it up from there. And it kicks out the hypoblast cells, it creates a new embryonic endoderm layer. This one has a strong AKA called the definitive endoderm. I've seen that around. So now it's the second germ layer we just made. So we made we made the mesoderm. Now we made that was the first germ layer. A second germ layer is the endoderm. And yeah, here's that picture again. We got our cells, our bottle cells, our mesenchymal cells have made it all the way down here, and they've kicked out the native hypoblast cells, and then they've morphed back in to these epithelial cells. So we really went from epithelial cell to mesenchymal cell back to an epithelial cell for this layer. Okay, fun facts. Endoderm forms the roof of the secondary yolk sac, right? So the yolk sac is right under here. Amniotic cavity would still be up here. We just have all the walls cut off. There's the amnion, just a little stub of the amnion there. Okay, there's the wall there, Heusser's membrane. Or remember there was some weird layer that came down that was unnamed. Those are probably those cells. Heusser's is probably one deep to that. If you don't know what I'm talking about, go back to my previous videos. So as we said, to make an endoderm cell, you have to complete the cycle of epithelial to mesenchymal to epithelial conversion. We kind of talked about that already. Okay, here's Larson. Larson has it backwards, I think, but this is a drawings from Larson, day 14 and 15. But it's kind of just cool how to give you an idea. So Larson believes that the mesoderm forms last. He thinks that the cells go through the cranial region, pick up tons of nodal, have energy. They go all the way down here, and they kick the hypoblast cells out to create the endoderm. And then around day 16, he says that these bottle cells, they come down, they go through the more caudal portion of the primitive streak. They don't get a lot of nodal, so they don't have a lot of power, and they fill the in-between here with mesoderm. Now, I don't think that's correct. I really think that this happens first and then that happens second, like Carlson. But Carlson says it kind of happens at the same time. That's probably what happens. Okay, formation of the ectoderm. So we got one more job to do, and this is pretty much the same as I already said. Epiblast cells, they no longer move toward. When the epiblast cells stop ingression and everything is still, the remaining epiblast cells, genes get turned on and they transform into embryonic endoderm or ectoderm. And so that's our last germ layer. So we just made all 3 germ layers. Should be noted that the ectoderm forms first cranially, so this isn't all uniform. It forms during the cranial first. So the process of gastrulation actually goes in a cranial to caudal direction, according to Larson anyway. But it is, all the authors keep pointing this out, these epiblast cells are the stars of the show, right? Because they end up forming all 3 germ layers. They get a little modified, but the epiblasts are the magic cells. Okay, and there's the 3rd layer again, completed. Trilaminar disc is now done, and we got our nice ectoderm layer, we got our middle mesoderm layer, and then we got our bottom layer here, which is the, remember these used to be the hypoblast cells, that's the endoderm now. Hypoblast cells got kicked out to form some of the extra embryonic mesoderm. All right, a little more work to do. And again, this could have happened anywhere in the time period I'm talking about, but it happens really close to the first couple days of week 3. Oropharyngeal membrane and the cloacal membrane need to be talked about real quick. Talk about the cloacal membrane first, cloacal membrane first. It happens about the same time the prechordal plate is formed. This is not mesodermal cells. So some genes get turned on in the epiblasts that are caudal, way caudal, and they thicken into this weird thick tissue called the cloacal membrane. So we've seen these pictures before. Whoops, did I got the wrong? No, I cut off the wrong arrow, didn't I? Cloacal should be going right to here. So that's going to become the anus, and it forms the vaginal opening, and the urethral openings will be formed from this tissue eventually. Okay, so this will become the future opening of the anus, urethra, and vagina. That doesn't happen until week 7, and the cells of this tissue also bind epiblast and hypoblast together. So I don't have a side view really for this, but this tissue, the epiblast and hypoblast cells bind so strongly together that when mesoderm is being laid down, it can't get in here. So this region, and the same with the oropharyngeal membrane, these are not trilaminar discs, these are bilaminar because they have bounded. The epiblast and hypoblast have binded so tight together that you can't form mesoderm in there. The oropharyngeal membrane, almost the same thing. About the same time as the cloacal membrane forms, you get a cluster of cells where the epiblast and hypoblast bond really tight together. And and this is going to occur right above, more anterior, more cranial to the prechordal plate. That's called the oropharyngeal membrane. Take a wild guess what that's going to become. That's going to become the opening to the mouth eventually. Okay, like the cloacal membrane, these cells fuse together very tightly. No mesoderm can get in there, so it's a bilaminar disc in that region. Will become the opening for the oral cavity about week number 4. Okay, so technically we are all done. Now, some authors, they're all over the place with regard to gastrulation. You think you could figure out what days gastrulation occurs between. Larson says we're done with it, but Moore is a little not so conclusive, and Langman is not so conclusive. So some say that gastrulation continues into the formation of the nodal cord or neural tube, but I'm going to go and say it's done at this point. based on Larson and that nice little chart that he gave us. He's the only one who seems to organize it. So, okay, so what have we accomplished with gastrulation? We made a primitive streak and we made 3 germ layers. We also made a, what did we make? We made a cloacal membrane, an oropharyngeal membrane, and the prechordal plate. We also made all those 3 during gastrulation as well. All right, thank you for watching, and give me a thumbs up if you liked the video, and we'll keep the next topic, which is going to be formation of the nodal cord, and we're going to talk about formation of the neural tube and get into the subdividing of the mesoderm to paraxial mesoderm, intermediate mesoderm, and lateral plate mesoderm, and things are going to start getting crazy. All right, see you in the next video.